तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Right, so let me start today with orbital angular momentum, and then I return to this problem of adding two angular momenta, which is what we had started, and I promised I would show you what the rule for adding quantum mechanical angular momenta is like and why it differs from the classical case because of the non-commutativity of various operators. But let us go back a little bit and talk about orbital angular momentum. I have in mind a particle, quantum mechanical particle of mass m, moving in space in 3 dimensions, and then we know the orbital angular momentum about the origin is defined as L equal to r cross p. That is our definition, and there is no problem with ordering whether r should be on the left or p should be on the and p should be on the right or vice versa. There is no problem of ordering here because this cross product involves, if I resolve it into Cartesian components, a given Cartesian component of the position and some other Cartesian component of the momentum which are not conjugate pairs, and therefore there is no problem with moving them about either way. So this is the definition. And of course once you write this operator acting on a position space wave function, recall that P should be replaced by minus IH cross del when acting on position space wave functions. That is our rule for quantum mechanics. Now what sort of wave functions would correspond to eigenstates of the angular momentum? This is what we would like to answer, and of course we know that there are commutation relations. Li Lj is IH cross epsilon ijk Lk. Okay. We already know this, that there exist these angular momentum commutation relations. We also know from our general study of angular momentum that the operator L squared, which is Lx squared plus Ly squared plus Lz squared, commutes with each of the generators, commutes with all components of the angular momentum, and in fact L squared and any component of L, let us say Lz, they can be simultaneously diagonalized, and the eigenstates of the system of the orbital angular momentum could be written in terms of two quantum numbers. So we have L squared acting on these eigenstates which are labeled by two quantum numbers L and m. I will use this notation instead of little j because I am now talking about orbital angular momentum, and this is the standard notation. This is L times L plus 1 h cross squared on Lm, and Lz on Lm is h cross mh cross Lm. Now from a general theory of angular momentum, all we know is that this little l can only take on the values 0, half, 1, 3 halves and so on. But if it is orbital angular momentum, I mentioned that L can only take on integer values, not half odd integer values, and the reason is buried in the single valuedness of wave functions, because after all if I now talk about this angular momentum as the orbital angular momentum of a particle moving in some potential, then the wave function of this potential as a function of position coordinates must be unique. At every point you must have a unique wave function. This automatically will imply, as we will see shortly, that L must be an integer. Now let us go back and write down the Schrodinger equation, and then we come back to this and ask what sort of wave functions you would have. So this is a particle moving in a potential and I would like to exhibit spherical symmetry in this problem, only then is the total angular momentum conserved, otherwise it is not so interesting to resolve things into spherical harmonics. So what condition do you need classically in order that you have angular momentum conservation? What sort of potential should it be? It should be a central potential. So let us look at a central potential. So V of r, so in a central potential. Okay. Now what is the Schrodinger equation for this system? Well, the Hamiltonian is p squared over 2m plus v, which is a function of little r alone, and when it acts on position space wave functions, then the eigenfunctions or the stationary states of the system would obey something like minus h cross squared over 2m del squared plus v of r acting on phi, that is my symbol for the wave function, the stationary state wave functions, and this would be a function of r theta and phi, because I would like to use spherical polar coordinates, it is most convenient to do so. This is equal to E phi of r theta phi. That is my time independent Schrodinger equation for the stationary state wave functions in the position basis. Now what we need to do is to resolve this del squared in spherical polar coordinates and then see if we can solve this problem using the fact that V of r is a function of little r alone. So what is del squared in spherical polar coordinates? This is equal to 1 over r squared delta over delta r squared delta over delta r plus 1 over r squared sine theta delta over delta theta sine theta delta over delta theta, these are standard formulas, plus 1 over r squared sine squared theta delta 2 over delta phi 2. That is del squared written in spherical polar coordinates. Okay, this is a very common thing, it is a standard expansion of del squared in spherical polar coordinates here. Recall that it is also the same as saying that this quantity here, this p squared, could also be written as p radial squared over 2m plus angular momentum squared over 2m r squared plus v of r. You could also write it in this fashion. By definition, you can resolve the square of the total momentum as the radial part squared plus the angular momentum part squared. Notice it is a 1 over 2m here and 1 over twice the moment of inertia here, 2m r squared. So dimensionally this is okay. Now of course we can identify what pr squared is. This portion comes from pr squared, right. So it is quite clear that since p goes to minus ih cross del or p squared equal to minus h cross squared del squared, it is immediately clear by definition it follows that pr squared is minus h cross squared over r squared delta over delta r squared delta over delta. That is the position space representative operator, differential operator representing the square of the radial momentum, and the rest of it is the angular momentum apart from this factor here, because that is already sitting here. So it is clear that L squared has the representation 1 over sine theta delta over delta theta of sine theta delta over delta theta plus 1 over r squared sine squared theta, no r squared. There is also a very important L squared minus h cross squared. Okay. L has dimensions of Planck's constant, so L squared has dimensions Planck's constant squared, and that is it. This multiplies everything. this fashion. Okay. So this is the way you arrive at the so called radial Schrodinger equation, which you must have studied in quantum chemistry when you studied the hydrogen atom. It arose by saying that this system has some energy eigenstates and the wave function is of this form, and then for del squared you simply resolve it in spherical polar coordinates and you got this guy here. Now what is the next step? The next step is to try to solve this partial differential equation by the simple method of separation of variables, and this is going to work in this present instance because V of r is not a function of theta and phi. So the radial equation will separate out from the angular equation. Right now we are interested in the angular part. So the next step is to say let phi of r theta phi be equal to some function of little r alone, some r of r say, multiplied by some function of the angular variables alone. And what is that function? Let us give it some name. So let me for the moment call it f of theta and phi. I would like to keep theta and phi together, the two angular variables together, because the equation that I have, this portion has both theta and phi sort of mixed up in it, whereas this is clean, this is just separated out, r is separated out. So for the moment I would like to keep it in this fashion. This function may further factor into a function of phi and a function of theta, but at the moment I just keep them together in this fashion. Then if I apply this operator on it, it is immediately clear that in the position basis these states Lm, because I know that whatever it is, the eigen states of this square of this orbital angular momentum must be labeled by the quantum number L and the number m, and these are the eigenstates, and I know the properties of these states. I know what L plus does on it, L minus does on it, and so on. So I use this fact here, and what does that tell me there? It says that this function f of theta and phi must satisfy the equation. If I plug it in, if I put it in here, L squared acting on that guy must give you L times L plus 1 on the other side. So this f of theta phi must satisfy. Now what is this f of theta phi? F of theta and phi, you will readily identify, is simply taking the orbital angular momentum state Lm in the position basis. That is all it is. So I should really put r vector here, the bra vector here, but it does not depend on the radial coordinate at all, it only depends on the angular coordinates. So let us call that theta phi. In fact, let us not even do that. Let us say in spherical polar coordinates this is r and this unit vector is n, and that is an arbitrary point. So an arbitrary point in space is labeled by a radial coordinate little r and two angles theta and phi, and let me call those two angles the unit vector n, because that specifies the direction. It is just a little bit of saving of notation. Instead of writing theta and phi, I write unit vector. So this stands for theta and phi. So what I have is this, and that is all it is, this f of theta and phi. And what kind of equation should this satisfy? It says L squared acting on that, so minus h cross squared delta over delta theta sine theta delta over delta theta plus 1 over sine squared, or there is a 1 over sine theta here too, minus h cross squared 1 over sine theta delta phi 2 acting on this function of theta and phi, or f of n if you like, must be equal to L times L plus 1 h cross squared on f of theta phi, because this is an eigenvalue and I take the bra here, an inner product with the unit vector n, and this is all you get, and h cross squared cancels on both sides, and you can bring this over here and change signs completely. So what is the equation satisfied by this quantity f? It is 1 over sine theta, this fellow, so let me write this down, plus L times L plus 1, this whole thing acting on f of theta phi must be equal to 0. So that is the partial differential equation obeyed by f of theta comma phi. Any angular dependence on the wave function must obey that equation. Okay. But it is clear that this operator here depends on L, and for each L there are many values of m possible. So it is very likely that this function here depends on both L and N and L. It is labeled by L and M. Just as in the one dimensional particle in a box problem, when we solved the equations for the stationary states, we found out that the energy eigen states phi were actually labeled by a subscript n, quantum number n, and the solution was sin n pi x over L for different values of n. So let us put that label in, and standard notation here is y Lm of theta and phi equal to 0. This quantity, this function is called a spherical harmonic. It is a solution of a homogeneous equation which involves theta and phi, and it is some function labeled by two quantities L and M. Now we still don't, yeah.
How do you take that, when you take the ket vector, it should be n, L squared, L comma n.
N, so this is a number, so this becomes n L m. But in the position basis, the action of L squared is given by the action of this differential operator, because I replaced it by p by minus I h cross del, so that automatically said del squared, the angular part, is simply that operator. So this is the same as saying that differential operator acting on n bra n ket L m, which gave you this differential equation, and the solutions are called spherical harmonics, and we can simplify this. This is now a standard problem in ordinary differential equations. We further separate into, assume that YLM trial solution would be a product of a function of phi times a function of L, and then it turns out that these YLMs of theta phi are in fact of the form e to the I m phi times some constant times p Lm of theta, where this is a normalization constant. This quantity here is called the associated Legendre polynomial, Legendre function of order L. There are actually 2L plus 1 of them. For each value of L, this m runs from minus L to plus L. Yeah, must be of the form.
Why have you said f of theta comma phi is that?
Why have I said it's equal to this? Why have I said it's equal to this? Well, the actual wave function phi of r theta phi is actually shorthand for r theta phi or r vector with the state, with the abstract state, whatever it is. That's what this thing stands for, the wave function. But now I'm saying this r is labeled by r theta phi, and if I assume that this function is a product of a function of r and a function of phi and theta, then clearly only the angular momentum part, only the angular part is affected. L and m affects only the angular part, and that's exactly what has happened here. So the actual state vector, some horrible state vector, would really, think of the hydrogen atom problem. The actual state vector would be labeled by NLM with a principal quantum number as well, and this guy here is what I call phi of r theta phi. but this becomes a product of a function, radial function, times ylm of theta phi. So I simply said that as far as the angular part, orbital angular momentum part is concerned, this does not play any role, it is only L and M, and instead of r I replace it with theta and phi, or this unit vector n. M does not appear explicitly here, not yet. So the whole point is this equation has many solutions, and for a given value of L it has 2L plus 1 solutions, independent solutions. And of course in quantum mechanics the general state was always a linear superposition of all the independent solutions. So you have to take that into account. Just as in the particle in a box problem, when you solve the eigenvalue problem, you found a very simple eigenvalue problem there, you discovered however that the solutions were of the form sin n pi x over L. So you had to label the solutions by this quantum number n and then make the statement that if these fellows formed a complete set, a general solution is a linear superposition of all these solutions, all the individual independent solutions. The same thing happens here. So I have written down one angular solution. If I were to write down the actual wave function, then I would have to sum this over all the allowed values of m in general for a general state, and then fix all the constants depending on my initial state or whatever, boundary conditions and so on. Okay. So is this clear? This is how Legendre's equation makes its appearance. It simply separates out the angular part. You still have to now deal with this question of what does the radial equation look like, what is the equation satisfied by this, I will come to that in a minute, but the angular part looks like this. And the reason why spherical harmonics are important is because this is going to be the angular part of the wave function for any central potential, for every central potential, because independent of what V of r is, what its functional form is, this is going to always be the angular part. So it is a standard thing, and therefore one should first solve it and write it down. Now these things here, I presume you are familiar with properties of Legendre polynomials, I will write them down in the problem set. They are PL of cos theta, PL sometimes written as PL of cos theta, I have just written it as theta, not good notation, I should have written PL of cos, so that is standard notation. Y L0 of theta and phi is in fact equal to square root of 2L plus 1 over 4 pi, that is a normalization factor, PL of cos theta. Okay. I do not remember offhand the normalization constants for YLM in general, but I will write it out in the problem set. Okay. So remember again that PLM or YLM is really shorthand for 2L plus 1 such functions where m runs from minus L to plus L. And in the special case when m is 0, it just reduces to the original Legendre polynomial, otherwise it is called the associated Legendre polynomial. Okay. So it is some derivatives of the original polynomial. Okay. So we actually have our eigen functions explicitly in the position basis YLM. So we could write this whole thing out in the position basis, and it turns out then that L squared, which is that crazy differential operator, acting on YLM gives you this constant times YLM, and LZ acting on this YLM gives you MH cross YLM. Now you could ask what happens to Lx and Ly, what do they look like in spherical polar coordinates? Well, that is just an exercise in polar coordinates, conversion from Cartesian to spherical polar coordinates. So let me write those expressions down. Remember that L is r cross p, so Lx is equal to ypz minus zpy. These two commute between themselves, so it does not matter which order I write it in. Ly is equal to zpx minus xpz, and Lz equal to xpy minus ypx. Now you could ask, what do these guys look like in the position basis? Suppose I am going to act on functions of r theta phi, what do these fellows look like in spherical polar coordinates? This goes over into, again the root is by saying P is equal to minus IH cross del, that is all you have to do. P is represented by minus IH cross del, then this Pz is delta over delta z with a minus IH cross etc. But now I have to convert from Cartesian coordinates to spherical polar coordinates, and when I do that the answer turns out to be minus IH cross delta over delta phi. But Lx and Ly turn out to be a little messier, and the reason is, as you know, spherical polar, by the way this is the reason why we insist on quantization in the z direction. You notice I wrote sigma 3 as a diagonal matrix, not sigma 1 or sigma 2 by convention. The reason is it arose from here. The original problems that were solved like the hydrogen atom, were solved in spherical polar coordinates, and in spherical polar coordinates you give a special status to the polar axis which conventionally is taken to be the z axis. So that is how the z axis got singled out, and not surprisingly Lz just turns out to have an extremely simple form here, but not Lx and Ly, these turn out to be more complicated. This is minus IH cross, and if I remember this right, I used to at one time, so let me see if this is right. Minus, I will check this out and let you know, it is minus sine phi delta over delta theta minus cot theta cos phi delta over delta phi, and this is minus IH cross, I know there is a plus here, cos phi delta over delta theta minus cot theta sin phi delta over delta phi. Please check this out against textbooks, if it is right it would be a miracle, but it is okay. And del squared, of course L squared is this. So if I take that operator, those operators, and do Lx squared plus Ly squared plus Lz squared and simplify, I should get this. So as you can see, these transverse components of the angular momentum are quite messy, they mix up theta and phi in a messy form. This is cotangent, whereas Lz is very simple. Yeah. Okay. And now you can also see where you got the e to the power Im phi from, because it is clear that you must have Lz acting on Lm must be equal to mh cross on Lm, therefore Lz acting on n Lm in the position basis, so that is minus IH cross delta over delta phi of this guy here must be equal to mh cross n Lm, and it is obvious that the solution to this is e to the Im phi. So that is how the angular part, the azimuthal part, the part that depends on phi, just turned out to be a phase factor e to the Im phi. But of course the full del squared involves also Lx squared and Ly squared, which is messy, these combinations, and therefore you got this non-trivial Legendre polynomials. Now why should L be an integer? The answer is Ylm of theta phi must come back to itself if theta increases by 2 pi, if phi increases by 2 pi under a full rotation. So about any arbitrary axis, if you rotate and you rotate by a 2 pi, you should get right back to the original wave function. It turns out that requirement makes L an integer. Because of the single valuedness of the position space wave function. So that is the requirement, that is the reason why it becomes. There are other reasons which one can give. If you start with r cross p, then it is automatic immediately, but if I start with an abstract angular momentum, then little l is a quantum number for the square of the total angular momentum, could be integer or half odd integer, but this single valuedness makes it, forces it. If you start with r cross p, then by definition when I solve these differential equations, this differential equation L squared acting on some function of theta and phi equal to whatever L into L plus 1 or the same function, that is an ordinary, that is a differential equation, and there is a theory of second order differential equations which tells you that the solutions have to be single valued, unique, etc. So the uniqueness theorem for the so called Sturm-Liouville problem, which is what this reduces to, imposes already that L must be an integer. Okay. Please notice that the half odd integer values of L, they do not come about from any differential equation. We did not write down any differential equation for those cases, we just said this is an abstract state vector in angular momentum space for this angular momentum states. We never wrote down differential equations, so they do not come from such differential equations, they are not position basis representations at all. So that is an extra input. The spin degree of freedom of an electron has nothing to do with spatial wave dependence, it has nothing to do with its dependence of the wave function on r theta phi. That tells us that really when we describe an electron, in addition to the quantum numbers n, l and m, which come from the r theta phi degrees of freedom, if you like, 3 degrees of freedom, 3 quantum numbers for instance in the hydrogen atom, in addition to these there is this spin quantum number, and that implies that S is half, and there is a corresponding Lz component or Z component here, which I also denoted by m, but I have used that here, so let me put it as m sub s here, and this is equal to plus or minus half. So in addition the states of the electron are described by this extra quantum number, the spin quantum number, which has nothing to do with its positional dependence as far as the wave function is concerned. So what does that mean? It says that really these are the states of the electron, and since we know the spin is half for every electron, we do not write this, we just write this. So you have really 4 quantum numbers to describe the electron in a hydrogen atom. For instance, the principal quantum number, orbital angular momentum quantum number, the so called magnetic, which tells you the eigenvalue of Lz, and the spin, whether m sub s is plus half h cross or minus half h cross. Therefore when I take the position space representative of this, I really have 2 wave functions. I really have phi, and they are labeled by this NLM, and they are functions of this r, but you should also say whether the spin is plus half h cross or minus half h cross, you have to add that. So what one does is to say okay r, and then I should put spin up for instance, and I should put phi NLM r and spin down for instance. And very often it is convenient, since clearly what is happening is the position space wave function is a member of L2 square integrable functions of the space coordinates r theta phi. But there are 2 such wave functions, one corresponding to Sz equal to plus half h cross Eigen State and the other to minus half. So it is convenient to combine both of them and put them as a column vector, because the spin space is 2 dimensional. So you write them as a column vector here, and then you write this whole thing, I could write this as NLM of r by definition. So this guy here is a square integrable function as far as r is concerned, but it is really a column matrix with 2 elements, each of which is square integrable, and these are the wave functions corresponding to the 2 spin states. So it immediately becomes clear that if you are describing the wave function in position space or momentum space for that matter of a spin s particle, you really need 2s plus 1 wave functions, each of which is square integrable. So you get a multi-component wave function, and each component would obey the position space Schrodinger equation, and the spin degree of freedom is independent, completely independent. This is how in the hydrogen atom you get this two wave functions always, and you have to include both of them in a complete description of the hydrogen atom. So I hope this makes it clear to you that the spin degree of freedom has nothing to do with any mechanical motion, it has nothing to do with the r and the p and the position and the linear momentum or anything like that. It is an internal degree of freedom of the system. You should treat it mentally in the same footing that you treat the rest mass of the electron or the charge of the electron. These are internal properties of the system, and they do not arise due to any spatial dependence of the wave function. Okay, this is also the reason why we yesterday dealt with just this or just that separately. Now let us talk about addition of angular momenta to look at the total angular momentum of a particle which is now in some potential and therefore has some orbital angular momentum about the origin and has a spin degree of freedom as well. Yes, because I did not work this out fully, but I said that if you use this differential equation, L squared on this guy must also, so L squared acting on the wave function f of theta and phi must be equal to minus h cross squared L times L plus 1 f of theta phi. This is a second order differential equation, and theta runs from 0 to pi, phi runs from 0 to 2 pi. That differential equation one can show must have solutions which are unique for every theta and phi in the physical region, and that imposes the requirement this single valuedness of this f of theta phi can only be satisfied, it turns out, if L is an integer. Okay. Now this comes from the theory of differential equations, which I have not gone into, but the fact that you have this differential equation, second order differential equation, automatically imposes this. But you can ask, where did this come from? This came from saying that P is represented by minus I h cross del. It really came all the way from there. So the fact that, and where did that expression come from? It came by saying that L is R cross P. So the fact that I imposed, I put in the fact that the orbital angular momentum is special, it is not just a general angular momentum, it is representable in terms of the dynamical variables of the system, the position and the momentum, linear momentum. That has led finally to the fact that the wave function must be single valued. The orbital part of the wave function must be single valued. In turn, that puts a condition on L. Just as when you solve, we will do this if time permits, when you solve the hydrogen atom problem, the requirement that the wave function be square integrable automatically quantizes the energy of the system. So it constrains the possible set of solutions in exactly the same way this imposes single valuedness. Yeah. Pardon me?
Are the coefficients of the spin states equal?
Are the coefficients equal? Now what would this be? What would the physical significance of this be? The answer is, let me use a little bit of shorthand notation. Let us just call this plus and minus, okay, so that I write this out more easily. Okay. This plus corresponds to plus half h cross and minus corresponds to minus half h cross. Then the physical meaning of phi plus or minus of R NLM whole squared, this would be the probability density of the particle at the spatial point R when the system is in the quantum state described by NL and M and the spin state has plus half h cross, and similarly for the minus. Now there is no requirement that in general, without further information, that these two coefficients should be equal at all, right? They are just two probability densities, and if you do things to this electron, if you do things to the system to polarize it in one direction or the other, or you let it evolve, this can certainly change with time. But they are the two independent amplitudes for the two spin states, and you can't reduce it any further, they are independent. They may satisfy a total normalization condition, but they are actually independent. Now look at what happens to the total angular momentum. Good point. There is no Schrodinger equation for the spin. Why has that happened? The reason is I did not put anything into the Hamiltonian which would distinguish between the two spin states of the system, but suppose I put a magnetic field, then it is a different story. Now let us see what happens if I take this hydrogen atom or this central potential problem and put a magnetic field, constant uniform magnetic field say, then this Hamiltonian has an extra term plus, and we saw if it is an electron, mu Bohr magneton times B times sigma dot n, where this n was the direction of the magnetic field. Now of course it is very clear that you couple to the spin degree of freedom, but that sigma acts on either the top or the bottom half of this guy, of this column vector, and then now you are in a different shape altogether. And it is immediately clear also that in general the equations for the differential equations for the up and the down states would actually be mixed up, would get coupled to each other, because this sigma would put, when it acts on the up state there will be a portion from the down and vice versa. If this thing is in some arbitrary direction, this can certainly happen. So not only is this particle going to be moving in this potential, but it can also undergo a spin flip transition, and then of course you have a different problem altogether. So that is a good point. The reason it did not show up here was because I did not put anything in the Hamiltonian which would couple to the spin. The moment I put it in, then it is a different story.
So in absence of a thing, both phi plus and phi minus.
Otherwise I would say the system is unpolarized, then the probabilities should be the same because nothing is going to happen and so on. Now what is the total angular momentum? The total angular momentum J is L plus S. But you see the components of L and the components of S commute with each other completely. Therefore J squared is L plus S the whole squared, which can be written as L squared plus S squared plus, what should I write, L dot S or S dot L or both, it does not matter, in this case it does not matter. So I write this as plus 2 L dot S, because the various components Li Sj equal to 0. So J squared is given by this, but you see if I am talking about an electron, S squared, no matter what state of the system, what state the electron is in, you are always in an eigen state of S squared with eigenvalue S times S plus 1 H cross squared. So that portion, this portion of it becomes redundant, I mean it is just a constant added to the whole thing. So this is L squared plus S times S plus 1 H cross squared plus 2 L dot S. We know what happens here, this fellow we are going to be labeled by little l, and this is first order in L, so all the three components would contribute, no problem there, and you can quantize along any axis you like. So the addition theorem in this case becomes rather simple because these two commute with each other, there is no problem, etc., and this is always for an electron, this is 3/4 H cross squared, whatever. But we would like to do this in general and see what happens if I add two angular momenta J1 and J2. They come from different origins, I do not care where they are from, and I add these two and I would like to know what is the resultant here. So let us face that problem, let us see whether we can add two arbitrary angular momenta. So what is my problem? I start with an angular momentum J1, this has components J1x, J1y, J1z, etc., and this satisfies commutation relations J1i, J1j equal to IH cross epsilon ijk, J1k, where ijk are the Cartesian components. I have another angular momentum J2, and that satisfies exactly the same sort of relations with 2 replacing 1 here, and these are independent of each other. So I further have J1i J2k equal to 0. So my physical system has a total angular momentum J which is made up of two mutually commuting quantum mechanical angular momenta J1 and J2, and I would like to know what are the angular momentum eigenstates of my system. I can't do naive vector addition J1 plus J2 because of the following problem. I know that this little j, this j is characterized by a quantum number little j1 say, then the states of the system are given by j1 and m1, where little j1 is a quantum number which is 0, half, 1 etc., and would the j1 squared would have eigenvalues little j1 plus 1 times h cross squared, and m1 is the corresponding eigenstate of j1z. So j squared, j1 squared is j1 into j1 plus 1 h cross squared, the same state j1 m1, and j1z on j1 m1 is h cross m1 on j1 m1, okay. And I assume that little j1 is given to me, okay, some given quantum number, okay. Similarly for 2, j2 also does this with little j2 replacing this. Now what's the maximal set of mutually commuting operators so that I can start writing states down? Well, if these two fellows do not talk to each other, these two angular momenta, they commute with each other, then the states of the system must be of the form j1 m1 direct product with j2 m2. Those are the states of my system, angular momentum states. I have to tell you what is the j1 doing and what is j2 doing. And how many states of this kind are there for a given little j1? 2j1 plus 1. So this is 2j1 plus 1 and that is 2j2 plus 1, and this is the dimensionality of my angular momentum space. So let us take a specific example, spin half electron, and let us say it is in the orbital angular momentum quantum number state L equal to 2, the d state of the electron. Then little j1 is L, that is 2, 2 2s are 4 plus 1, that is 5, and the other guy is the spin state 2j plus 1, 2j2 plus 1, that is 2. So you have 10 possible dimension, 10 is the dimensionality of your angular momentum space. Alright. So what are the mutually commuting observables? In this case they would be j1 squared, j1z, j2 squared, j2z. That is my set of maximally commuting, mutually commuting observables, and the space dimensionality of this Hilbert space is 2j1 plus 1 times 2j2 plus 1. Every state can be written in this basis as a superposition of these states. So let me give it some shorthand notation. I will call this j1 j2 m1 m2. Let me use shorthand notation for this, just call it j1 j2 m1 m2. And for fixed little j1 and fixed little j2, essentially it is only m1 and m2 that change over the different states. M1 takes 2j1 plus 1 values, similarly for M2, and the total number of possible states is this product here, okay. But you see I can do this in a different way. I can find another set of mutually commuting observables which is the following. If j is j1 plus j2, then j squared equal to j1 squared plus j2 squared plus twice j1 dot j2, again because j1 and j2 commute with each other, so it does not matter what order I write them in, and this quantity here, this total angular momentum squared can be quantized, that too satisfies commutation relations. Capital J I with capital J sub j is I cross epsilon I j k etc. So I can find another way of doing this, and that is j squared jz, because that commutes with j squared. And what is the definition of j sub z? By definition is j1z plus j2z. That is the whole idea of adding these two vectors. You add each component, j squared. And what else? And what else? I claim there are two other operators which you can find from all these fellows. j1 squared, j1 squared and j2 squared would commute with these operators, because look at what happens to j1 squared commuting, whether it commutes with jz or not. j1 squared is j1x squared plus y squared plus z squared, that commutes with every component of j1, so it certainly commutes with this, and j1 has nothing to do with j2, so it commutes with this. Therefore this operator commutes with this as well as that. It commutes with this too, because it certainly commutes with itself, it does not have anything to do with this guy, and this is a linear combination of components of j1, each of which this commutes with. So certainly this commutes with this, it commutes with this, and so does this, and they mutually commute. So this is another possibility. I can choose the independent maximally commuting set of observables in two different ways in this case. Notice I cannot add j1z to this guy, because the moment I do that, what happens if I add j1z to this? J squared has this nasty fellow sitting here, so this involves j1x, j1y and j1z, and that will not commute with j1z. So I am not allowed to add j1z here or j2z. Similarly I cannot put anything from here into that, I can't put jz into that. So these are two independent ways of doing things, and each of them must give exactly the same answer. So what does that mean? Oh, by the way, I have to prove to you, and we will do that in a second. So what does that mean? If I choose this set, then my eigen states are labeled by j1, j2, m1, m2. This is what we did earlier, it is just direct product states. But if I choose this, what are the eigen states labeled by? They are labeled by the eigenvalues of this maximal set of commuting observables. So these are labeled by little j, whatever that guy is, little m, whatever that is, and then j1 and j2. Since j1 and j2 are common, let me put that first, that is the standard notation, j2, and then put jm. This is a different basis. It is like choosing rotated coordinate system, two different bases. But we still have to answer the question of, does this form a basis, what are the allowed values of j, what are the allowed values of m, we do not know that at the moment. All I am saying is this transforms like the square of an angular momentum, therefore its eigenvalues have to be of the form j times j plus 1, and I have called that j here, and similarly this is m. At the moment this is all I know. I have to find the relation between these two bases, and I have also to show you that, for instance, if I have a state of this kind, m must be equal to m1 plus m2, must be equal to, that is any single component the quantum numbers simply add up. I have to show you that this is the case. So let us do that in the following way. You agree that this is a state in the angular momentum space of the system, therefore I should be able to write j1 j2 Jm equal to a summation over all the other possibilities in the basis of states of this kind, some coefficients times J1 J2 M1 M2 times some coefficients. What should the summation be over? M1 and M2, because little j1 little j2 are fixed, are given to you. So it is a summation over M1 and M2, two summations times some coefficients. But actually the way to find the coefficients is to say, look, this guy forms a basis and therefore j1 j2 M1 M2 is the unit operator, that is the unit operator in this space, this whole guy, because it is a complete set, it is a unit operator. Now you will see the power of this Dirac notation acting on the original state Jm. I want you to recognize clearly that these kets are in the original basis and these kets are in the new basis that I am trying to find. So if you like, you call these blue kets and call those red kets or something. I mean, I don't, this M1 M2 has a different status from this Jm, but I don't want to clutter the notation, but it is not even necessary. Okay. So you agree that these are just numbers, those coefficients, and these are your basis vectors. This set of coefficients, a set of complex numbers in general, they transform from one angular momentum basis to another. I have still to show that the Jm basis is a basis, I have not done that yet, but they are coefficients, they are overlaps functions. These quantities, this set are called Clebsch Gordon Clebsch-Gordon coefficients. Our job is to find them. For given little j1 and little j2, I have to find these Clebsch-Gordon coefficients. My first claim is that this fellow equal to 0 unless m equal to m1 plus m2 is equal to 0. I claim this. And now you will see the power of this Dirac notation, because I proved that almost effortlessly in the following way. I simply say, all right, let us take this state j1 j2 jm and act on it with one of these suitable operator. So let us take j1 j2 jm, I act on it with jz minus j1z minus j2z, and I put this bra here j1 j2 m1 m2, this operator, and I sandwich it between these states. This state here is an eigen state of j1z and j2z with eigenvalues m1 and m2. This state is an eigen state of jz with eigenvalue m. So this fellow I cleverly operate on the right, but these guys I cleverly operate on the left. So that gives me m minus m1 minus m2 on this Clebsch j1 j2 m1 m2 j1 j2 jm must be equal to 0. And that can only happen because jz is j1z minus j2z, so this by definition. So the right hand side is 0, this must be 0. So either this guy is 0 or else that Clebsch vanishes. So it immediately shows that the Klebsch-Gordon coefficient is 0 unless m is m1 plus 2. So the power of this notation is unbelievable. So that is why I said any component like the z component just adds up linearly, but the angular momentum itself has this quantum rule of addition which is non-trivial. So that is our first statement. The next thing I have to show is that this little j actually can take on a large number of values all the way from mod j1 minus j2 to plus j1 plus j2. I have to show that next. So I do that next time, but this is the way we are going to derive the addition rule for angular momenta, and that is it. I mean, once that rule is set in place and the whole thing is finished. So you can see that addition of angular momenta in quantum mechanics is somewhat non-trivial. This is for 2 angular momenta, you get these Klebsch coefficients, Klebsch-Gordon coefficients. Now if you add 3 of them, you first have to add 2 and then a third one, and then you add 4 of them, it gets more complicated. These are called 3j symbols, 6j symbols, 9j symbols and so on. In atomic physics you need to use some of these symbols. People have gone up to 15j symbols, whole books have been written, volumes have been written. It becomes very, very non-trivial because the number of symmetries of these coefficients, they are called Raka coefficients, is very complex, very intricate, and has many fascinating connections with other branches of mathematics. So what starts out as a kind of practical thing in order to find out how quantum mechanical angular momenta add actually leads to a sub branch of mathematics itself in that sense. But I will get back to this and we will evaluate these Klebsch-Gordon coefficients in the simplest cases. Yes. Okay.